Okay, so we're here for some problem solving in two-dimensional kinematics. Two-dimensional kinematic problems are problems where the motion that you're trying to understand or describe is not generally solvable in terms of motion in a single axis, x or y, up or down, left or right, like we've been doing for the last little while. Instead, the motion is described in two directions, and that in turn makes the analysis a little more complicated. You have two sets of kinematic equations that you usually have to work with, and so we're going to go through a series of examples in order to examine how that's done. So our first example isn't particularly complicated. There are a multitude of different ways to do it, so I'll do it a couple of times here. This is the first time that I do it for you. We have my priceless Yugo, which we've encountered many times before. And let's suppose I'm driving around in the winter and I begin to slide on the ice. In the effort to recover from my deadly slide, I head diagonally through the intersection with an initial speed of v naught is equal to 10 meters per second. And the question that I'm asked to find is how far have I slid after 2.5 seconds in both the x and y directions, assuming that I initially started sliding in a direction that was 35 degrees above the x-axis. Okay, so there are many different ways to do this. Let me solve it in a slightly more complicated way than you need to, but it will illustrate some of the kind of basic precepts of solving two-dimensional kinematics problems. So the first thing we always do is I draw a coordinate system that is on top of a physical picture, so I can be clear about what it is that I'm analyzing and clear on how I'm setting up the problem. So I'm flying into an intersection, which I will represent by drawing a set of street corners here. So you can imagine this is an intersection in the town where you live. Okay, so that's my intersection, and I want to draw a set of coordinates on this. And so I'm going to draw both the x and y axes. And I will indicate the directions that I mean by plus x and plus y on those axes. And what the problem tells me is that I initially slide into the intersection along a trajectory that is 35 degrees above the x-axis. So my vector, my velocity vector, is diagonally through the intersection, where the angle with respect to those coordinates that I've drawn is 35 degrees. Additionally, I'm told that the speed, the magnitude of that velocity vector is 10 meters per second. I guess I was going pretty fast through that intersection. Okay, so that's all that I'm told. And in two-dimensional problems, very often, the very first thing that you do is you break every vector that you're given, or every vector that you need to know and can calculate, into its components. That is, into the individual vectors that point along the x direction and the y direction, that when summed, give you that vector that you were told. Now in this case, this is pretty straightforward trigonometry. I have the velocity vector there, and I know its angle with respect to the x-axis, so I'm going to use that angle to do a little bit of trigonometry and tell me that the x component of that velocity vector is simply the magnitude of the vector times the cosine of the angle that that vector makes with the x-axis. And similarly, the y component of this is the magnitude of the vector times the sine of the angle that it makes with the x-axis. Now I can numerically compute what those things are. Vx is 10 meters per second times the cosine of 35 degrees. And if I calculate that value, I get that it is 8.2 meters per second. That is to say, if I were to look at this 10 meters per second and imagine how much of it is contributing to my motion in the x direction. My motion in the x direction is 8.2 meters per second. Similarly, I can calculate Vy. This is again 10 meters per second times now the sine of 35 degrees. And if I work out what that is, the y component of my speed is 5.7 meters per second. Okay? So I have everything I need to know now. I'm going to write out a kinematic table. Now, because this is two-dimensional motion, I really need two kinematic tables, one for my x motion and one for my y motion. So I'll write out my kinematic variables as x, x naught, vx, that is the component of my velocity in the x direction, v naught x, my initial speed in the x direction, ax, my acceleration in the x direction, and time t. And there's a similar set that goes along with y. So this is y, y naught, vy, v naught y, ay, and t. Now, this problem is a constant velocity problem, but we go ahead and write out the full kinematic table as if there is acceleration, because we use the exact same set of kinematic equations for problems whether you have constant speed or acceleration. The constant speed problem, as we've discussed, is simply a special case where a is equal to 0. So let's fill in this table. The time that we're asked to evaluate the problem over is 2.5 seconds. That time is the same for both the x and the y motion. The acceleration in this problem is 0. We are traveling at constant speed, so in both the x direction and the y direction, the speed is constant, and so the acceleration is 0 meters per second per second. The initial and final speeds in both cases are the same. So I'm going to group those together so I only have to write it once. The speed is constant. And we've calculated up here what the values of the x and y components of the speed are. So I'm going to go ahead and put those in my kinematic table. The x component of the speed is 8.2 meters per second. The y component of my speed is 5.7 meters per second. Now again, here at the top of the kinematic table, we encounter one of those implicit assumptions that you have to make when you set up problems. That is, what is the initial position? We often choose values that are implied in the problem in order to make our life easy. And in this case, our life is made considerably easier in terms of algebra if we make the initial position for both the x and y direction the origin, as I drew it up here in my picture. So I'm going to put a 0 meters in for x naught and a 0 meters in for y naught. And what we're asked to find is what are the x and y values. Okay, so there are many different ways that I can do this, and probably the easiest way is to simply use the position kinematic equation. So let me just do it for x, and then I'll leave it for you to do with y on your own. So in this case, the kinematic equation for position is x is equal to x naught plus v naught t plus 1/2 at squared. Okay. In principle, there should be little x subscripts on the v naught x and the ax there. Okay, so in this case, I know that my initial position is 0 meters, and I know that my acceleration is 0. So this becomes a very straightforward equation that tells me that the final position x is simply equal to my initial speed, v naught x, times the time in the problem. So in this case, this is 8.2 meters per second times the time, which is 2.5 seconds. And if I multiply that all out, I find that the distance I have traveled in the x direction is 20.5 meters. Okay, so very similarly, in the y direction, there's an equation that will look like y is equal to v naught y times t, and that is 5.7 meters per second times 2.5 seconds again. And again, if I write that out, I find that I travel in the y direction 14.3 meters. Okay, so that is the complete solution to the problem that we were asked to find. That is the total distance I travel in x and the total distance I travel in y. Now, I said there's an easy way and a hard way to do this, or there's more than one way to do this, I guess is probably the better way to think about it. And so let's talk about the other way that we could have done this. The other way that you could have done this is you could have used that initial speed that you were given, which is the direction, the speed in the direction that I'm sliding, and the time to find the total distance that I traveled. So in that case, the total distance that I traveled is simply my initial speed times the time in the problem, which in this case is 10 meters per second, times 2.5 seconds, which is 25 meters. That is to say, I traveled 25 meters from the place where I started sliding along that diagonal line into the intersection. Now at this point, I could find the x and the y direction by using my trigonometry again, namely that if this is the distance that I slide along a diagonal line, I can then find the x and the y directions using the fact that that angle is 35 degrees. So in this case, the x direction, the x distance that I traveled is 25 meters times the cosine of that 35 degrees, and you should find indeed that is 20.5 meters as we computed above. And similarly, y is 25 meters times the sine of that 35 degrees. And what you should find is that is 14.3 meters. So we get the same answer doing it with pure kinematic equations, or we get the same answer if we compute it with a one-dimensional kinematic equation and then use geometry to find the components that we were asked to find. This is a useful technique for checking your work. If you realize there's more than one way to do a problem, you can do it both ways to make sure that you did the problem correctly. But in reality, some of you may have thought to do the problem this way, and some of you may have thought to do the problem this way, and it doesn't matter which way you do it. You get the same answer either way, so both of them are equally valid and equally proper solutions to a problem like this. Okay, so we'll do another problem. Good luck, and I'll talk to you later.